Okay. Good morning. Oopity. Wait. It's a little bit lower, this chair. So. Okay. To get in the picture, I'd like to discuss some topic, and that's about star formation. The theory claims that stars are formed from gas clouds, from hydrogen gas clouds. Well, okay. I've been thinking about this subject for a pretty long time, several years. Okay, what's going on in a gas cloud? And I thought it was a pretty hard subject to discuss, but it turned out to be very simple actually. And I've crossed some numbers, and I'm going to show you and discuss it with you in a moment. But you have to know some things. Why is star formation not possible based on the assumptions that the billion-year people assume? Why is it not possible? Well, you have to know some things about gas clouds in general. In the first place, there are only about 10,000 hydrogen atoms per cubic centimeter in a gas cloud. That's the density. Well, that's almost a vacuum. It's better than the best vacuum we can produce here on Earth. At least for a couple of years. I don't know if they can reach it right now, but that's what I have heard, that it's better than the vacuum that we can produce here on Earth. So 10,000 hydrogen atoms. Next to that, they have a temperature of about 100 to 1,000 Kelvin. So that brings along some speed with these hydrogen atoms. They have some speed due to the temperature they have. So these things are known. These things are scientifically correct, measured on those distances. I mean, from the light they emit, etc. They reflect some light from existing stars, and they can do some measurements about them. It's about the speed and about the composition of those gas clouds. That's all fair. That's good. But why is it impossible that stars form from hydrogen gas clouds? I mean, that's what theory claims, that gas clouds are swirling together to form a accretion disk and to make up a sun and stars and etc. etc. But why is that impossible? Well, like I said, I solved this problem, well, pretty simple actually. The thing is, what we see is that gases are leaking from planets, our present-day planets, from Earth. The Earth is leaking gases, and even the Sun is leaking gases. But also a planet like Jupiter, one of the biggest gas, is leaking gases, mainly hydrogen and some other gassy components. That made me think, hey, what is the gravitational pull of a planet or of a sun on a hydrogen particle? And what is the gravitational pull of a gas cloud to the center of mass of that gas cloud? And taking these numbers, which I just named, so 10,000 particles per cubic centimeter, which is a fact, a measured fact, and the distances. I mean, how much hydrogen do you need to compose one star with the mass of the sun? According to the model that the Big Bangers and the evolutionists and the million years folks have accepted as they think it's correct. Okay. So how much? Usually the theory claims that it takes about 10 masses of sun masses of gas, hydrogen, to compose one star with a mass like a sun, because the rest is blown away. But they need the mass to get the gas compressed, according to the theory. Well, why is that impossible? First, you have a temperature of 100 to 1000 Kelvin. That brings along some speed of the hydrogen atoms. Okay, but what is the gravitational pull, and is that gravitational pull higher than the average speed of a hydrogen atom in such a gas cloud? That's the thing that they have to overcome. Well, we're going to have a look at the forces that apply on hydrogen atoms in such a gas cloud. Well, I've crunched some numbers. The mass of hydrogen is 1.67 to the to 10 to the minus 27 kilograms. The Earth has a mass of about 6 times 10 to the 24th kilograms, and a radius of 6 million. Is that right now? Yeah, 6,300,000 some meters. We have to do everything in meters because the calculation of the force is also in Newton meters square. The gravitational constant is 6.672 times 10 to the minus 11th Newton meters squared divided by kilograms squared. So we have to do everything in meters and not in kilometers. So it's about 4,600 kilometers, which is about 6.4 million meters. Well, the Sun has a mass of about 2 to the 10 to the 30th kilogram of mass, and a radius of what is it? 600, say about 700 million meters. Well, a gas cloud, like I said, is assumed to have 10 times, at least 10 times the mass of a sun in order to produce one sun of one sun mass. So it's 10 times bigger in mass than the sun. Well, let's take for an average number 2 times 10 to the 31 kilograms. Well, if you take 10,000 hydrogen atoms per cubic centimeter, then you end up in a sphere of 6.6 approx times 10 to the 15 meter radius. Yeah? Okay. What is the force of a hydrogen atom pulled down by the Earth? Well, it turns out to be 1.65 times 10 to the minus 26 Newton. How hard does the Sun pull to a hydrogen atom? That is 4.6 times 10 to the 25th minus 25th Newton. And what is a gas cloud with this mass pulling at the distance of at the edge of the gas cloud? What's the force? Well, that's hydrogen to gas cloud. It's a force of 5.14 times 10 to the minus 38 Newton. Minus 38 to that power. So if you take the factor, if you take this as 1, which I've done here, what is the gravitational pull relatively to the other forces? Well, if you look at hydrogen to the Sun, then it's 9,000 billion times stronger the Sun pulls at a hydrogen atom. It's 3.2 times 10 to the 11th power stronger that the Earth is pulling a hydrogen atom to itself. We know that hydrogen atoms are leaving the Sun. We know that hydrogen atoms are going into space from the Earth. So apparently hydrogen is not pulled strongly enough to keep it on Earth and to keep it on the Sun. Yeah, we know that. This is a fact. The planets are leaking gases, mainly hydrogen. Yeah. Okay. So the star formation is in a problem because the powers that keep the hydrogen and pull hydrogen into a gas cloud is at least 9,000 billion times weaker compared to the hydrogen pull from the sun on hydrogen, and 2.3 times 10 to the power of 11 times weaker than the Earth is pulling hydrogen into the atmosphere. Okay, and it gets even worse. Suppose if you take the Earth and you take 1 kilogram here as a little dot, and you draw you drill a hole through the Earth, and you let that kilogram fall into that pit, yeah, to march to get it across the Earth to the other side of the Earth. Okay, what happens with the force on that kilogram? Well, you can calculate it if you don't believe me. The force is going straight down. If this is the Earth, this is the center of the Earth, this is the radius of the Earth. You drop 1 kilogram starting from here on the ground, and so that's the radius of the Earth, and it goes all the way to the center of the Earth, which is 0 in radius, of course. So what happens is that the force is dropping from 9.8 to 2 Newton. Yeah, which is the gravitational pull. If you calculate how much is weighing, something is weighing, and it drops all the way to 0 when it goes to the center of the Earth. Why? Well, the thing is, in here, the kilogram is pulled by all the gravitational mass the Earth contains. But the further it goes down into the Earth, all the forces of this will also pull back, so it equals to 0. All these forces of the Earth that is surrounding the kilogram is neutral. It's 0. But the inside of the core of the Earth is pulling. But since that part of the Earth is smaller than this part, the force is also smaller, and that's why it's reducing. So that happens also, of course, to the hydrogen atom in a gas cloud. So if you take 1 hydrogen atom to the edge of a gas cloud and you release it, then this is the force, 5.14 times 10 to the minus 38 Newton. And if you release it, suppose that this is the hydrogen atom at the edge of the gas cloud, the spherical gas cloud, then the force is dropping from 5.414 10 times 10 to the minus 34. It's dropping to 0. Yeah. So it gets even worse. So this shows this small calculation. I thought it was much more complicated, but it's not. The gravitational pull on a hydrogen atom in a gas cloud is, well, almost 0. It's too small to keep it in a gas cloud. Gas clouds are huge, enormous. This is about 0.7 light years. If you calculate all these numbers and you assume you accept the scientific correct number of 10,000 hydrogen atoms per cubic centimeter, then you end up with a approximately 0.7 light years as a radius for the spherical gas cloud. Well, taking that number, then you end up with a force of 5.14 times 10 to the minus 33.8 newtons. Sorry folks, but the hydrogen atom have a certain velocity due to the temperature they have. And the temperature is ranging between 100 and 1000 Kelvin in space, in empty space. So folks, these forces are far too weak to pull all the hydrogen into a star. It's not possible. It's a fairy tale. And the only other option is that God has created the stars, as the Bible is telling you. And well, that's what I wanted to share with you. So the numbers show it's physically impossible to make a star out of a gas cloud, a hydrogen gas cloud. That's what theory claims, that in the beginning there was after the Big Bang there was only hydrogen, and that hydrogen collapsed into stars. Well, you see folks, it's impossible. It is totally impossible. Okay, that's what I wanted to share. Hasta la vista.